Okay, we are back live here at HTE. We've learned vision. We've also learned about flexible feeding or flexible vision with Actinab when Universal Robots. As we said before, now we're transitioning into not just loading parts and loading parts, but we're also now with 3D high-end vision that gives you high read capabilities over a large area of parts. And with us today is Paul. He's the territory manager at LMI, and he's going to share the technology with us. So thank you, Paul.
Thanks, Mark. Appreciate it. Hello, everybody. Welcome. Thank you for coming. Thanks for the opportunity. I'm going to do a little bit of multimedia here today. So I actually have an example that I want to show, plus the presentation. So I'm going to sit down a little bit and maybe walk around a little bit. So stay with me. PowerPoint is not one of my favorite things. Death by PowerPoint is real, so it does happen, and I'm not going to do that to you guys, all right? I promise. The agenda, basically we'll introduce you really quick to LMI Technologies as a company, our Gocator 3D inspection systems. Talk a little 3D inspection versus 2D inspection, particularly how it fits in today's venue of robot integration. That's one of the examples that I'm going to go through for you. And then robot guidance common configurations. There's a couple of different ways to integrate with third parties, if you will, robots, PLCs, things like that. But there's two primary that we do with robots, and we'll go through those two. We'll take a look at some example applications, and I'll show a real quick short video that we have that highlights both common configurations. And then we'll finish up talking about integration and simplicity of using LMI locators with third-party devices, including. And then after that, we can go into Q&A. And if there's any questions, and hopefully you're still awake. So 3D scanning in general, it's basically a technology that measures things by shape, right? So it produces images and takes the shape, reproduces it of an item that is scanned. There's multiple ways to scan, but it doesn't matter. It's a three-dimensional image of your item or your object. What that gives you, in a sense, is a third dimension. So if you think of your cell phone cameras for the most part, or any 2D system, it's basically X and Y in a flat image. 3D adds Z. So you get height and depth along with the X and Y. That extra bit of information is the difference, and we'll show that. Where do you use it? Basically, in automation with robots is very typical for guidance as well as pass-fail. We'll show both those applications. Quality control, so 100% inline inspection by shape, measurement, volumetrics, things of that nature. And then optimization, slicing and dicing, anything where size and shape make a difference. You think of food and volumetrics. I need an 8-ounce slab off of this 10-ounce brick. 3D does that type of stuff perfectly. About LMI Technologies. So we've been around for over 40 years. Got our start back in the 1970s in the lumber industry. Basically doing saw cut optimization over large logs as they come into these basically shanties, if you will. They're a room with open walls. And they bring in 40-foot logs, which is basically tree trunks that have been trimmed, and they need to optimize or needed to optimize every board inch of that lumber as it came through. That's where we got our start. It's still a very large portion of our business, really second only to consumer electronics as far as where we're living and the number of units that we sell. 3D's been around for a long time, and LMI's been in it in a big way. We've got over 400,000 sensors installed. We own over 100 patents on 3D inspection and inline inspection. With over 350 employees, we're headquartered in Vancouver, Canada. So this is a new headquarters, relatively new headquarters for us. So we moved from Delta not long ago over to Burnaby. So I think we've been here probably 3 years now. If you ever get a chance, you're in Vancouver, by all means, stop by and see LMI. It's a really cool place. And you're welcome. So we have a global presence. So we're headquartered in Vancouver. We have 11 regional offices around the planet. 2 of them are located in the U.S., one in Detroit, one in Cupertino, California. We have distribution globally, such as the guys here at HTE. We have roughly 60 different distributors in 40 different countries around the world, and offices and support centers to support those. So our flagship product lines are Gocator. So it's our in. It uses a couple of different technologies and a couple of variations of it that are available. There's over 80 different models to choose from. So when we look at everything that we offer for 3D inline inspection systems, we feel it's the largest offering of anybody on the planet. We'll talk a little bit about it. We start out with our single point 1300 series displacement sensors. So these are basically one single point laser along with a camera that's built into the unit. It's pre-calibrated at the factory, and it has a single point of sensing, if you will, that can be sub-micron resolution and a few millimeters deep, or go out 2 meters and be half a millimeter of resolution, and basically everything in between. So you'll hear that a lot as I go through the different models that we have, is that just the breadth of offering that at different levels of resolution and field of view is how they are depicted, if you will, and how the price points are set up with them as well. So if you go from left to right here on the slide, the 2100 series is our VGA line profile sensor. This is where we have, it's got the camera and the laser built in and pre-calibrated into a single unit. One thing to mention here, there's no extra lighting, no extra lenses needed ever. So it's, as opposed to 2D, where you've got to worry about all that type of stuff and whether they stay in focus and if your selection was proper and anything like that, you don't have any of that with LMI 3D. So it's all built in, it's done for you. Pick the unit that fits the application by field of view and resolution, and you're done. So the 2100 series is our entry-level sensor. It's got 640 points of X resolution, and I like to jump around, as I mentioned. So what I want to do is jump up to the LMI website, LMI3D.com, and here you can go in and we have a product selection list as well as just the item, the products as they're itemized. We started with the 1300 single points. You can select on those and it comes up and gives you all the specific details to those. The Gocator 2100, which is a line profile sensor at 640 across X. And all the different models that we have here, 7 different variations, if you will, everything from a 26 millimeter wide field of view and a couple of microns of resolution, all the way out to 49 inches and about a millimeter of resolution. The cool part about the way LMI goes to market along with our partners here at HTE is we single price, for the most part, per family. It's why the resolution of the sensor, that's really about it. So everything in this family, if you will, are all right around $6 grand. They're all the same, or just a little less than that. They're all the same price. Pick the one you need, and it doesn't change the price of any of them. And that holds true pretty much until you get to the very top end specialty units that we make that are optimized for things like glass scanning and whatnot. So they're priced a little bit different just because the technology is a little bit different. But it's really simple and straightforward. So these guys all around 6K, and as I mentioned, everything from 20 millimeters to 49-inch wide field of view, and pick the one you need. The next model family is our 2300 family. You'll notice that they're almost identical when it comes to the resolution in Z and then the field of view that they scan. The difference with these guys is it's the next level up. It goes from 640 points in X to 1 megapixel imagers in 1280. So price doesn't double. I know you were wondering, but it doesn't. It goes from right around 6K to a little over 9. It's about $9,600. Pick any one in the family that you need. All the same price. Next up would be our 2400 models. These are the 2 megapixels, high performance, high resolution, 1280 points in X to either 1500 or 2000 or right around 1900 points in X. So you notice that we're doubling that resolution point of sensitivity across our profile. So we have 5 different models here. And this is our specialty model on the outside, or the far end of the 2490. Actually has a 2-meter wide field of view. So where we use this guy, I'm going to show you a part of the video here in a little bit where it's used to actually sit over the top of an automotive line, and a car comes underneath. It creates a 3D scan of the top of the car in order to do model identification, placement, and position of the vehicle on the carrier. So it's a fairly large item. All these guys are right around 12K. Next we go up to our 10 kilohertz. So this is everything I've talked about so far, besides the point profilers, are in the 5 kilohertz range, which is pretty common when it comes to laser profile speeds. These guys are twice as fast. So they're at 10 kilohertz speeds. They're 2 megapixel imagers. I have one set up on a gantry in the next room if you guys are interested in taking a look at the performance. I can max out the speed of my index, which is probably right around 200 mils per second. It's got no problem keeping up. So very fast, high performance 3D, high resolution. So these guys, the smallest field of view you get to is about 14 millimeters wide, but you're at a single micron or so of resolution. So 14 mils wide, 1 micron. And then from there it goes all the way out to 100 mils wide, which is the unit that I have here. We're in that 9 to 10 micron range there. High performance, high resolution. After that, we have our structured light sensors. So this is a little different technology. I'm going to walk you through that in a little bit, but there's only 3 models of that guy. They start out with a really small field of view and high resolution at 6 to 7 micron range again. It's a little different technology to implement that. It uses, it takes images of stationary objects, so they have to be still as opposed to something moving on a conveyor line. And we'll talk a little bit more about that, but there's 3 models of that guy. Or actually 4 if you count the 3520, which we just released not too long ago, which covers an 8.5 by 11 inch sheet or area, if you will. And those guys range in the 12 to 19 grand range, depending on the unit. And last but not least, which isn't necessarily used in robot guidance or applications, is our line confocal sensors. These guys do spectral analysis over multi-layers. They're very specialty item, if you will, for things like consumer electronic applications where they're doing multi-layer stacks or lens stacks or screen stacks for touch screen evaluation. This technology has the ability to actually do multiple layer scans in a single scan and use color spectrum to basically separate out those layers and do sub-micron analysis on it. Not necessarily a robot integration or guidance thing. I'm not sure how that would fit. So let's talk a little bit about the technologies that technologies we're using. Laser point profilers have a laser and a camera built into each unit, pre-calibrated again. And LED snapshot sensors have 2 cameras, so they're stereo imagers. If you look up and the bottom is a separate camera, an individual camera, if you will, and then an LED projector rides in the center of the device that creates the image. For laser triangulation, basically it's for moving objects, things that move. Either you can move the sensor over an item and create an image, or you move the item through on a conveyor, so to speak, and whatnot, in order to create the 3D image. So moving items, lasers, point profilers, or profilers. Stationary items, snapshots. So it basically uses the LED projector to send out what's called a fringe projection. So it's a series of anywhere from 12 to 2 dozen projected series of dots. They call pseudo-random dots that the system assesses through each acquisition, and then pieces together the 3D model of your part. So has to be stopped anywhere from a quarter second to several seconds, depending on how in depth the images that you're taking, the resolution, the exposure settings, things of that nature have a direct impact on the amount of time. But stationary items, that's where the snapshot sensors come in. So we combine both 2D and 3D image data into all of our technologies. So you'll notice in the center is basically the contrast image. It's black and white, but it does provide for a good level of detail. And what we do inside is we actually make that along with the 3D height map information in order to perform basically metrological level inspections down at the micron level. So the imaging, it's not just height maps, it is 2D and 3D together. And it produces very high grade or high quality images. So Gocators are all-in-one devices. So they come complete, a web server built into it. All you need is a device running a web browser, Firefox, excuse me, and an Ethernet connection, gigabit Ethernet, to connect up to it. And from there, it serves up all the tools, all the I/O configuration through that served up interface. And at the end of that, if you want to leave your whatnot connected and use it as an HMI, you can do that. Or you can remove it altogether and just rely on the onboard I/O and communications of the device to run your application and integrate it. So all in one, everything comes with it. There's over 153 different 3D tools and functions that come on board every Gocator. So lots of horsepower to perform lots of different inspections. And as I mentioned, they're 3D. So if you want to look at, I was talking about an application the other day where we were looking at countersunk holes. Well, they want to know what the bevel of the edge is from the top outer OD to the bottom ID. And they want to make sure that both those ID and OD are within spec, and they want to know that the level, excuse me, or the angle of that bevel is accurate. We have a tool called countersunk tool that literally does all of that. It goes out, finds the hole, gives you all that information individually. You can pass or fail on all of it. So just an example, 150 plus built-in 3D measurement functions. So let's talk a little bit of difference between 2D and 3D. This is a typical application where it really stands out, where if you look at this analysis, in this particular part you're looking at, it's flat black, right? So there's not a lot or any color contrast on it whatsoever. A 2D system, if this part moves around, it's going to be almost impossible to use a 2D system to find any surface anomalies on this, unless it's kind of a scratch that creates contrast in the image itself that can then be found through edge detection. So if you look at the picture on the right is the actual contrast image of that part. You can see in the center that there are dents that we put in it intentionally without marring the surface in order to basically show this is where the difference really is between 2D and 3D. What 3D does is it uses that onboard laser or LED projector to create the image, the actual surface image itself. Adding that Z height data, whether it's the depth below the surface or the height above it, you inherently get that in the data on your image. And it makes all the difference. For specifically for this application, it's obviously clear that 3D would be way out. So areas or applications where image contrast or part contrast and color either change a lot or there's very little or no variation between good or bad. 3D really does well, where you can get that volumetric information or that thickness information, that Z height data. Once you get that, basis, and that's kind of where we're going on this next one. And I will jump into LMI offers for free download an online emulator, or offline emulator, I should say, that runs on a PC. So it's free of charge if you go to LMI3D.com and you look for download the emulator. You can download it and run it on your PC. What is it? It's actual working Gocator on a PC with all your tools, along with 3D inspection scenarios. So if you want to play around with a Gocator and get familiar with it, work in the tool set, set it up, you can download the simulator. It comes with sample files in it and images in it that you can play around with tools with. It's also fully capable of using a host port on the PC to interact with other devices. So if you wanted to actually run through a scenario of images, get results out of it, and say port it to another PC or to a PL, you can actually do it off the emulator. So it's pretty cool, pretty functional deal. And this is all free, so LMI doesn't charge at all for that. What you'll see is that this is a familiar image. It's the actual image that we took with one of our snapshot sensors of that dented plate. And that's not showing very well in the contrast image, right? If you think about it, if that plate turns at all, even if, if you were dark field lighting that, as that angle changes, it's going to change, and it's almost impossible to use a 2D system to catch up with that. In our case, if we can see it, we can produce it, and we can measure it. So as long as it's visible to the system, I'm trying to get a good image here. A good way to show you, so you can kind of see the damage on the plate. But as I have added a couple of tools, one of those is basically a surface blob tool. As you see, it's actually going out, and I've told it, find anything that's below my normalized surface. Once again, remember, we get that height information in our image, so it knows. So all I got to do is just tell it, hey, anything a tenth of a millimeter or less below my normalized surface, that's got to be a blob. Go out and mark it. It does that. I can also do it the opposite way. Anything above that surface, go out. What is it? What's the value, right? So what do you do with it? Well, I could pass or fail on it really easy with the standard, digital I/O that's on board. Let's say this was a polishing application or a filling application, right? So you're trying to surface something automatically, going to mount sand it or polish it or fill. You can do that localized here as opposed to just doing the entire part. I want to go to the last guy here. So this is the image with the cells above. You see it's counting 3 of them. And you also notice that I've sorted, and I can sort these by size or position. And in this case, this is the largest one here. Now, I can actually export that into another set of tools. So I've got an X and Y position in an area that I can use to direct a robot in 3D space if I want to over my part surface. Or I can perform additional functions on it, volumetrics and other things, by just taking this image, or portion of the image that's segregated out, and placing it into another tool. So you see, there's my damaged area. And here's all of its 3D information. The XYZ center point, its width, its height, and any angular information that may be critical to it if you were going to send that off to a robot to grab it at a certain point. Features, capabilities of 3D over the top of 2D. All right, let's talk about robotic system configuration. So there's 2 primary ways that 3D systems or RD systems get integrated with robotic systems. One of them is considered an eye-to-hand calibration, where they actually mount the unit stationary over the top of a conveyor or a bin or something. The robot is completely separate, and it calibrates into the workspace. So that's considered hand-eye calibration, or I'm sorry, eye-to-hand calibration. Opposite of that is taking the sensor and mounting it right onto the actual 6-axis arm, and that's considered hand-eye. All right, much more common in 6-axis world, if you will, to go this route. We support either one, so no problem. And I'll talk a little bit more about that later. But those are the two primary ways. Another way is that they would actually, if I back up one here, in the hand-to-eye world is on the bottom here, as you can see. They have the sensor just side, and the robot's actually driving parts presenting to the sensor that then performs the assessment, pass, fail, go to good bin, go to bad bin, or rework. All right, jumping into some of the applications. This is where I want to show you guys this short video. So it's specific to an application that uses 3 Gocators. So if you see the white arrow at the top on the left-hand side, that's actually that the large 2490 series I told you about that has a 2-meter wide field of view. That's the guy that's looking down, that's getting the 6 degree of freedom position of the vehicle. And then sending that down to the KUKA robot, which also has, if you look on the right, it's kind of hard and blurry because it's basically a moving picture, but there's 2 Gocators mounted on the end of arm of that KUKA. And what it's doing is it's going down and it's going to up to 6 different positions along that car body as it's going down the line and measuring the gap and flushness of all of the panels. So it starts around the headlights and the hood, it goes down the fenders, and ends up on the tail lights and the trunk. So I'm going to show that.
At LMI, we are excited to be able to provide our automotive partners with cutting-edge gap and flush measurement capabilities. For the configuration seen here, we are using one downward-facing, ultra-wide field of view Gocator 2490 to determine the 6 degrees of freedom of the vehicle. That information is then relayed to a KUKA robot arm, allowing our buddied Blue Line Gocator 2440s to make detailed gap and flush measurements. Buddied sensors are networked to automatically generate a single, high-accuracy 3D scan of the target. This configuration also solves for any potential occlusions on the scan target. Scanning and inspection happens continuously and with no external computing required, all while the vehicle moves down the assembly line. Our Blue Line laser sensors are specifically designed to measure shiny or specular surfaces. This makes them especially suited for gap and flush measurements. Measuring surfaces like headlights, windows, and glossy white or black paint can be a challenge for traditional red line laser sensors. Red line laser sensors work better on lower reflectivity or matte surfaces, particularly on fast-moving targets. However, for specular or shiny surfaces, the red laser light becomes distorted, resulting in a speckle effect. In contrast, the shorter wavelength of the blue laser sensor produces much less speckling, resulting in lower noise levels, typically by a factor of 2 to 3 compared to red laser sensors. Using 2 networked blue laser sensors allows the client to scan deeper into the gap, generating more complete and precise measurement data. The process of combining and aligning multiple sensors is simple with our built-in alignment procedure. With the combined 3D point cloud dataset, we can now do our gap and flush measurements on the sensor in real time. Depending on the surface quality, our system can capture up to 60 measurement points per minute, taking 0.5 to 1 second per measurement point, including evaluation. These scans are extremely detailed, measuring not only gap distance, a 1/10 of a millimeter, but also the shape, smoothness, and curvature of the surface. With this data, many measurements, including calculations and pass-fail decisions, are made, allowing for a high level of quality assurance. Every Gocator sensor leaves our factory after undergoing rigorous factory calibration, assuring accurate measurements directly out of the box. Our sensors are compatible with many major robot brands, including Universal Robots, Yaskawa, KUKA, Kawasaki, Fanuc, and ABB. Hand-eye calibration, which translates our sensors' 3D data to the robots, is simple and built into our sensors. Using our wide field of view Gocator 2490, along with our paired Blue Line 2440s on a robot arm, we are able to provide a comprehensive, inline, hand-to-eye robotic vision solution for gap and flush inspection. If you would like to learn more about our 3D sensor technology and what it can do for you, visit our website at lmi3d.com.
All right, pretty neat, huh? Fast, too. Anyway, the gap and flush, two different systems, one directing the robot from above, basically where you get into the eye-hand calibration, and the other end of arm, so which would be relative to the hand-eye calibration. So both of the examples in a single application. Additional applications, 3D robotic guidance, vision-guided manufacturing. In this instance, basically inserting roof panels onto a vehicle. So the Gocators are mounted below the robot arm and the jig that's holding the roof, and it basically does the finding position of the roof panel prior to getting welded on. We also do windshields, so very similar application. Material dispensing, so adhesive bead. Think about following, either leading or following, if you will. So if you want to go out and you want to determine the placement of the or where it's supposed to be, you can lead it. And then you want to assess where it's been placed after the fact, you can lag or trail it. So similar to weld seam. So we do weld seam and weld bead inspection as well. So seam is basically guiding the stitching prior to the weld. So it's looking for each of the legs and the center point to determine the best stitch, and then general pick and place, discrete part manufacturing. So here it's mounted off robot, looking at products for pass-fail inspection prior to final packaging. Go, no go. Food processing, we do an awful lot in food processing, but for the robotic side, there's actually some applications where we're doing saw cut optimization, the packaging side of things, distribution, sealing, containers, and whatnot. That's going to be in the next one here. On food. Palletizing and depalletizing. In this example, basically they've got the system set up on the top left corner, and there's multiple box types that each type has to be stacked consistently in its own pallet. So it recognizes which, and the robot is then told where to place it. We do a lot in logistics as well. Gocator Integration, we are a UR certified partner. So we do offer free download from our website as part of our tools and utilities, the UR cap. So if you are UR, that's a tough one to say. If you are a UR robot user and are looking to integrate 3D inspection in, we support both on-robot and off-robot calibrations with our cap. There's videos at on our LMI3D.com YouTube channel of that take about 20 minutes to walk you through the setup once you have, at which point it's actually scanning and directing the robot where you want it to go. So it's actually a really neat, streamlined way, an efficient way to get 3D vision and robots together. On top of that, we support a whole host of other robots, as Jonathan had mentioned in the video. And yeah, I think that kind of concludes where I'm at. I hope I didn't
go too great. Did great. Yeah, thank you very much, Paul. Appreciate
Thank you.